Okay. So, like I said, the inductor stores energy in the magnetic field, in a magnetic field. Okay, so we'll see that. Okay, so an inductor resists an EMF source, battery from establishing an instantaneous maximum current in the RL circuit. So what this is saying is, so when you close the switch, you see as the current is increasing, this inductor induces an opposing EMF, and it's fighting this increase in current. So the battery has to work to establish a current in the circuit. And when it's doing work, it's storing energy. Just like you do work when you're lifting up an object, and by lifting up an object, what have you done? Because you've done work, you've stored potential energy in it. Just like that, this battery in establishing a current has stored energy in this inductor. So the battery does work to establish a steady current, and in the process stores energy in the inductor. So here was the differential equation governing the current when you close the switch, E minus IR. Okay, so let me go to, okay, so here was the, okay, you close the switch, the differential equation was E minus IT by R minus L di by dt equal to 0. Okay, so we'll rearrange these terms. Okay, and then we'll multiply E times I. So this is I square R plus Li di by dt. Okay, why did we do that? Well, this is the energy being supplied by the battery. This is the energy being dissipated by the resistor. Okay, so this is your earning, this is your spending. What is this? This is your savings. Okay, so here's the energy supplied by the battery. Energy supplied by the battery. Here's the energy dissipated by the resistor. And this is I di by dt. So what we're going to do is we're going to write it like so. D by dt of 1/2 Li squared. Okay, d by dt of I squared will be the 2 will cancel that, and you get this term. Okay, the derivative of that is this. Okay, so again, this is equal to I squared R plus d by dt 1/2. I'm just rewriting this. Okay, so this is energy rate at which energy is delivered by the battery, and rate at which energy is dissipated, rate at which energy is stored. Okay. So that's what, so power delivered by the battery is E times I. This is equal to rate at which energy is dissipated in the resistor times the rate at which energy is stored in the inductor. Okay. So hence rate at which energy is stored in the inductor is given by this. U is the energy stored in the inductor, which is 1/2 Li squared. Okay, so inductor is 1/2 L squared. L is not and AL. It's all known, so 1/2 mu naught N squared AL I squared. And inside of hello, can you guys hear me now? Are you guys there? Did we get it looks like we had gotten kicked out of the meeting for a second or something. All right, anyway, something happened. All right, so here we go. So the magnetic field inside this was given by mu naught n I. Okay, so in this inductor, the energy stored is given by that. So we are rewriting all this. 1/2. I'm using big I and small I interchangeably. So I is B mu naught over N. Mu naught N square AL, and I is so B square mu naught square N square. So the energy stored in the inductor, N square cancels, can be written as B square over 2 mu naught times AL. This is the volume of the solenoid. Okay. So the energy stored is the volume times this fellow. So this is the energy density. This is the energy per unit volume. Per unit volume. And this is the energy stored in the magnetic field. So we saw in the case of the capacitor stores energy in the form of electric fields. And here we are seeing that an inductor stores energy in the form of magnetic fields. Okay, so the moral of the story is anytime you create an electric or magnetic field, you're storing energy in those fields. Okay, and that's what this thing is showing you. So the energy density or the energy per unit volume stored in the magnetic field is B squared by 2 mu naught. Okay. All right, so now we'll come to the most important application of inductors. Inductance, we'll talk about transformers. All right, so this says losses are minimized when power is transmitted at highest possible voltages. Voltage step up and step down transformers are used for power transmission. So what we're talking about here is the following. Okay, so here is the US, and our current model is you have generating stations, and homes. These diagrams are not to scale, and you got to transmit power over thousands of miles. Okay, so for instance, this could be the Hoover Dam, and you're getting electricity from the Hoover Dam. Okay. Now this transmission losses, you want to minimize transmission losses. Okay. And so to minimize transmission losses, you have to transmit power at high voltage. So in the US, I believe we transmit at around 800,000 volts. Okay. So to minimize this, to minimize transmission losses, you have to transmit power at high voltages. So the question is, how do you go from your generating power at low voltage, and how do you go step up to high voltages? And that's what transformers come in. So transformers are this is a magnetic material. Okay. You have input coil. This is the input voltage, and this is all AC voltage. Here's an output coil, and this is output voltage. Okay, so what happens is this is an AC current. As the current direction changes, the magnetic field direction changes. Okay, and there's a changing magnetic field that's coupled through this, And as the magnetic field changes, it induces the voltage in the output voltage. Okay. And output voltage, this is N2, N1 is N2 by N1 times input voltage. Okay. N2 is the number of turns in the output coil, N1 is the number of turns in the input coil. So if the number of turns, if the output turns is 1,000 times greater than the input number of coils, the output voltage will be 1,000 times the input voltage. And that's the idea. Okay, so voltage across the secondary coil in a transformer, V2 is N2 over N1 times V1. Okay, so you can, if N2 is greater than N1, then it's a step-up transformer. If N2 is smaller than N1, it's a step-down transformer. Okay, so here you use step-up transformers, and here you use step-down transformers. Okay, oops. So here you use step-up transformers, and here you use step-down transformers. You don't want 800,000 volts coming into your house, do you? Okay, so in all towns and cities, so step-down transformation doesn't happen in a single step. You will see a bunch of transformers in every city, central transformers, and then you'll see transformers near your homes on those poles and stuff like that. Okay, so that's what the transformers do. Okay, they're stepping up and stepping down voltage. Right, now we'll see an oscillating circuit, an LC oscillator. Now, this is an extremely important thing. It's obvious wouldn't work. So see, let's see, already have it. So let's go. Can you guys hear me? Hello, guys. Okay. It looks like Zoom has been kicking us out periodically. It's been slightly unstable today. Okay. All right, so here we go. So here is an electrical oscillator. So in this diagram, what you see is this capacitor is being charged. And so energy is stored in this capacitor in the form of electric fields. You can think of it that way. And so this is an ideal LC circuit. There's no resistance to dissipate the energy, meaning no resistor to convert this energy into heat. Okay. And so you turn on the switch. And here's what's happening. So energy is going from electric fields to magnetic fields and back and forth. So energy is stored in the capacitor and then the inductor and back and forth. Remember, that's what we needed in an oscillator. In an oscillator, you needed two devices that store energy in different forms. And you're converting energy from one form to another. The initial example we'd seen was mass attached to a spring. Here it's potential energy, kinetic energy, potential energy. Okay, so energy was being converted from one form to another. The same thing is happening here. Uh, the same thing is happening here. Energy is being converted from electrical energy to magnetic energy, energy stored in magnetic fields. Okay, and this is the basic LC circuit. Okay, and this is at the heart of all wireless devices. Okay, this is what is this LC circuit is what's used to pick up a signal. So when you grab a signal from air, this is the basic tuning circuit at the heart of everything, of all wireless communication. Okay. All right, so here's the LC circuit. Okay. So again, in this diagram, we'll go through this again slowly. All the energy is in the capacitor. Now both of them have energy, and after a quarter cycle, all of the energy is in the inductor. Both of them have energy, back to all the capacitor having all the energy. Both of them have energy, all the inductor having energy, and so on. Okay. So the energy oscillates back and forth between the capacitor and the inductor. Okay, here's the differential equation governing the behavior of this system as it oscillates. See, as long as there's no resistor present, the total energy present in this system remains constant. So there's the energy in the inductor and there's the energy in the capacitor. That's the total energy. And the time rate of change of that will be 0, okay, because the energy will remain constant. And then you can take the time derivative. You can set this equal to 0, but what you'll get is a nonlinear differential equation, and you don't want that. Anyway, so you take the time derivative of that, and you get this equation for the charge on the capacitor. Okay, so this is the differential equation governing the charge on the capacitor. And this is exactly the equation. Okay, so let me. So let's go to our slides. Oops. Okay, so. All right, so you guys remember for a mass attached to a spring, xt, the position of this mass was governed by this differential equation. Omega square xt equal to 0. And now for this oscillator, okay, the charge on the capacitor is governed by exactly the same equation. LC. Okay, so you see the same differential equation is appearing here. And so omega square is 1 over LC. Omega is square root of 1. Okay, so that's the natural frequency of oscillation of this guy, okay, this circuit. All right, anyway, so you see two very different looking systems, but they're governed by the same differential equation. Okay. So that's why you take your differential equation classes. Okay. All right, so there's the differential equation governing the charge on the capacitor, and there's the solution. So the charge in the capacitor changes sinusoidally, Okay, and the current also changes sinusoidal. Okay, so there's the natural frequency of oscillation of this guy. Okay, and so this is the basic tuning circuit. So there is the capacitor and inductor. Unfortunately, resistance, you can't avoid resistance. There's always some resistance in the circuit. Okay, and so what you're doing is, so what this is showing you is the following. Okay, let's go back to our drawing board. So,
Professor Tolson, we're not looking at the screen. It has you.
I'm sorry?
We're not looking at the PowerPoint. It's just like your video.
How long has this been?
For a little bit.
All right, so why didn't you guys say something? Oh, well. Okay, how about now? Now
Yeah.
you guys, okay, so did you guys see this screen? I mean, did you guys see this when I was talking about this? All right, so let me repeat this. Okay, so here is this oscillating circuit, and there is the differential equation. What this gives you is Q as a function of time on the capacitor. The charge on the capacitor is a function of time. So there is the charge on the capacitor as a function of time, and you see it's oscillating sinusoidally, or okay, sine or cosine function. And similarly, the current in the circuit is changing sinusoidally. Okay. So this is the basic tuning circuit, and the natural frequency of the circuit is 1 over square root of LC. Okay. So here is the basic tuning circuit. There is the L, there is the C, and unfortunately you cannot avoid resistance, so there is the resistance. Okay, so here's how this thing works. So let's go to this again. So here is the capacitor. Here is the inductor. Okay. And this is a variable capacitor. That's what that arrow through it says. This is the antenna. Okay. All right. So again, this is the tuning circuit. That is tuning circuit that's at the heart of all wireless devices. Okay. So now let's say this is a radio at the heart of a radio. So here's one signal with frequency 1 with the, okay, so here's another signal with frequency, different frequency F3. Again, you guys get the idea, F4. Okay, so there are all these signals in the room competing for your attention. How do you pick out the ones that you want? What you do is you tune this circuit, you change the capacitor or the inductor, whatever it is. So in this, you're changing the tuning circuit such that this, you're adjusting the frequency of this to match the signal you want to pick up. So if F0 is equal to F1, that's the signal that you'll pick up. That signal will drive the largest current in the circuit. All these other signals will drive smaller currents. Okay, so whatever frequency you matched it to, that'll drive the largest current in the circuit, which is what you'll pick up. Okay. And then you send that signal to a processing circuit via transformer, so to speak. Okay, so the inductor talks to another inductor, and this is the processing circuit. Okay, so that's your radio. So again, this is at the heart of, this is the tuning circuit, and this is at the heart of all wireless devices. Okay, our lives would not proceed without this fellow right here. All right, so here's the differential equation with the resistance present. What resistance does is it converts energy into heat. Okay, so here's the energy stored in the inductor and the capacitor. And because of the resistance present, this energy is decreasing. So the time derivative of this guy will be negative, and there it is, minus I square R. Okay, so you can rearrange all these terms, and there's the differential equation for the Q, the charge on the capacitor. Okay, and all right, so here's what happens. So let me show this. All right, so what we have done is you initially charged the capacitor, and now what we're going to do is we're going to remove the battery. Okay, so we have stored energy in the capacitor, and now we'll let the capacitor discharge through this thing. Okay, so you see, with resistance present, if there was no resistance, this would oscillate forever. But with resistance present, the energy is being converted to heat, and all the energy from this circuit is lost and being converted to heat and being radiated away. Okay, so here's how the charge on the capacitor dissipates. Okay. And that's what we want to look at. And that's what so this differential equation is describing the behavior of this circuit. Okay, that's what this differential equation is doing. And so you can solve this, and that's what we saw in the simulation. The charge is dissipating like so. Okay, so the charge on the capacitor as a function of time is given by Q max minus, and the amplitude is exponentially decaying, and it's oscillating. Okay, so it's E minus R T by 2L. So if R were 0, this would be 0, and the charge would oscillate, and that circuit would oscillate forever. Okay, with the resistance present, the frequency of oscillation changes slightly by this amount. Okay, and the circuit is critically overdamped. If this term were greater than this term, this becomes imaginary, and that's called an overdamped circuit. And if this were equal to that term, then this would be 0. It would not oscillate at all. This was a critically damped circuit. Okay, the charge just goes to 0. All right, so that's a damped oscillator. Okay, anyway, going back to this is your basic tuning circuit. Okay, and when if you want to pick up a signal, what you do is you change the frequency, you match the frequency of this circuit to the signal you want to pick up. And then resonance happens. When the frequency of the driver matches the natural frequency, you set up large amplitude currents. Okay, so that's what's happening. All right, so we will stop now. That finishes the lecture. And I will let you guys ask questions.